All right, everybody. Glad to talk. So you're listening to SG2 in Space. Let's start out with that with your host, Shinga. We are the only weekly space show here in Houston. Apologies for not having one last week. We'll make that up. I will. So, in any case, I imagine if you are watching this live, you are seeing us on Facebook.com/The Shin Show. Be sure to follow me as well. It's called SG2 in Space nowadays, but back then it was The Shin Show. Can't change that on Facebook. On YouTube, search for SG2 on Space, and you should find it. Or you can go to, if you're, like I said, if you're watching live, we are a1.com, which is a website for Action One Media Group, which is where I'm sitting right now in the Action One Media Group studio. Okay, so, and, oh yes, very important, please support me at patreon.com/SG2 on Space if you like the show, patreon.com/letter S, letter G, number 2 on Space. Could really use your support, for the studio space and production, and take a look, so, okay, so once again, patreon.com/SG2 on Space. So without further ado, let's just say that today I am actually going to talk about, remember last time I talked about time, so today we're going to talk about the nature of reality. Leonard Kramer will be on, joining us shortly. If you recall from previous episodes, if you have seen any, he has been a recurring guest on SG2 on Space. And so he's quite knowledgeable about aerospace and physics and cosmology. So with this kind of topic, particularly on the nature of, say, reality, we're going to talk a lot about, say, quantum mechanics, which sounds like a hard subject, but if you boil down to it, it can be understandable to a degree. It's still quite confusing, can be. All right, so we're going to see if we can elucidate some of the mysterious factors, aspects of that. Instead of just a word you think, oh my gosh, I would never understand anything, let's turn it into something where, you'd be like, okay, I can see this. All right. So, yeah. Let's see. Should we get Leonard on, or maybe? And so how about this? All right. Let me give a quick what is it? Like, what exactly is quantum mechanics? How about that? So here's how it's going to work. I'm going to talk a little bit about it, and then I'm going to take a short break, and then we can have Leonard jump on. So, quantum mechanics is a fundamental theory of physics which essentially describes nature at its smallest, like on the atomic and subatomic scales, all right? So, before the development of quantum mechanics, we presented the world in a manner now known as classical physics. Of course, back then, there was just physics, right? So in the early 20th century, a lot of physicists actually thought that we have essentially explained everything, and there's going to be no more physics, so to speak, that there's no more that we wouldn't know. All right. However, it turns out that there were some weird things happening which could not be explained. So the first one, well, one of them, is the Albert Einstein's photoelectric effect. So this was back in 1905 when the photoelectric effect, just to give you a quick background, is emission of electrons or other free carriers when light hits a material. Okay, so in classical physics, light is treated as a wave, all right? So originally Newton treated it as a particle, but then later it's like, hey, it behaves like a wave, right? So now, if it behaves like a wave, then there could be a whole bunch of different energy levels. So you wouldn't, photoelectric effect, different light, you have more light hit a substance, it should have more electrons emitted. That's not what actually happens. It turns out you have to have certain energy levels to kick out something, and it's always the same energy of electrons that's kicked out. So it's quantized, okay? Hence, actually, one of the meanings of quantum, right? So there's a lot to this. Let's just say quantum mechanics, there's the energy is discretized, which means it follows at certain levels, okay? It's discrete numbers. Another thing that might be interesting is that it's based on probabilities. So for instance, if the basic one, say, is position and velocity, I believe. So if you you can never know exactly where something is. All right, we're gonna have to take a little break. I could go in this intro some more, but I think after this break we can bring Leonard on and talk about this in greater depth. All right, so break time. We'll be back shortly.
You know, some of the other things you got going on.
Absolutely. So thank you for having me. I feel like I'm in the presence of like celebrities.
It's just the shades, man. Shades.
So I think like 2000.
Growing up as a black kid in New Jersey, all I ever wanted to do was be a pro athlete.
Okay, we're back. All right, so you're listening to SG2 on Space, and today we're talking about the hidden nature of reality. And particularly, let's talk about quantum mechanics. So we have Leonard Kramer on. Leonard, can you hear me?
Oh yeah, can hear you real well. How you doing?
Hopefully you can. If you can hear me, say something.
I'm saying something.
All right, glad to hear your voice, Leonard. This is, as you know, this is the first show this year that has you on here, so it's great.
I'm excited.
Yeah, for sure. So
Yeah.
I try to give a little short intro to quantum mechanics. What would you I don't think I completely stated everything I was going to state. How would you describe it, and how is it different from what's known as classical physics?
Well, for me, the notion that at the very microscopic level, where the physics that governs how atoms and molecules and so forth come together is a different kind of physics than is classical. In other words, it involves things like random events that occur and the probability of things happening. And so I guess probably a lot of our listeners know that that there's a problem. There's a wave mechanics that's associated with it, and it's just a different way of dealing with the world, and in a way that we don't see at the large scale level. So it's not the physics that governs the planets in their orbits. It's the physics that governs how, for example, electrons configure themselves around atoms. And there's some very, very fundamental mysteries that occur that are at a very deep level that physics has been struggling with for 100 years.
So I'm going to briefly interrupt you and just say that so from what I've been reading, quantum mechanics incorporates 4 classes of phenomenon for which classical physics cannot account. One is what I just described before the break, which is a quantization of certain physical properties, for instance, energy. Another is, and we'll go into these, another is quantum entanglement, which I always thought was interesting. The third is principle of uncertainty. And the fourth is wave-particle duality.
Okay.
So, okay, continue.
Yeah, I would say that that's the case. The quantization really is a quantization that you're referring to is really a special case that occurs with bound systems. But generally, the issue has to do with uncertainty. All of this was worked out in about the first quarter of the 20th century by people like Heisenberg and Schrodinger and Einstein.
Leonard, can you describe the uncertainty principle a little bit? That's quite different from classical.
So what we've come to conclude is that if you have the knowledge of the position and the velocity of an object like an electron, you can't determine both of those to arbitrary precision. If you know the position, for example, with great certainty, then your velocity is utterly uncertain. And then there's also an uncertainty relationship between the time of an event and the amount of energy that is expended in that event. So those are the two main elements, and it's at a very deep level. So it's a very mysterious kind of thing.
So
about
macroscopically, say I see a car, right, that's driving along, and I can measure how fast it's going, its velocity, at any particular time, as well as where it's at, the position. Are you saying for on the very small scale, the atomic or subatomic level, you can never know both of them precisely?
You can't know them precisely, and the product of the uncertainty. In other words, if you're familiar with like a width of uncertainty. Like your position is good to a certain number of centimeters. So the product of that uncertainty, if you multiply the uncertainty times the uncertainty in your velocity, that can be no bigger than a certain constant called Planck's constant. I mean, specific, And so, so you know, most of your listeners are familiar with that.
I'm actually not sure if most of them are familiar with that, but no, that kind of makes sense. So to measure anything, Leonard, we keep talking about, we say measure, right? What does that exactly entail?
Okay. So that's controversial actually, because when the theory was articulated, probably pretty much complete by about 1930, there was a lot of interest in what it means to measure something, and one of the theorists was Niels Bohr, and he kind of came out with an interpretation that said when a conscious observer measures something, that it actually puts it in that state. So if you measure the velocity or you measure the position, the answer that you get at a certain level is the answer plus a little random thing. And that random thing is not understood by physics, I think. I assert. So they actually crystallized this whole theory onto the notion that a conscious observer affects reality. Now, in the past 50 years or so, that's kind of fallen by the wayside, and we now have this idea of entanglement, and there's a theory called decoherence. So it's believed that, well, let me back up. if you're familiar with the Schrodinger cat, Schrodinger's cat is either alive or asleep. So you put a cat in a box, and you have like some kind of radioactive decay that triggers a hammer that breaks a bottle that lets out sleeping gas. So the radioactive decay is determined by quantum mechanical probability. We can't tell you when it's going to decay, but it triggers a switch that then breaks a bottle and releases some sleeping gas, and the cat is either asleep or alive.
So
and when you,
go ahead, Leonard.
Right. So what's actually happening, what's actually believed to be happening, is there's a series of decoherences. In other words, when the system, this whole system is quantum mechanical, and so when the radioactive decay occurs, then it interacts with other elements that then spread this coherence to other elements of the system. We say it becomes more and more entangled, and in that respect, at the level of the observer, there's a kind of more than one world. So there's a virtual case where when I open the box and look, I see the cat asleep, or I see the cat, awake. Right. Well, I then become cohered with the system, and I can no longer communicate with the other world that sees the cat.
Let's take a step back. So, just for the sake of our listeners, I understand everything you're saying. But this is gauged towards an audience that maybe have a little bit of physics background, but quantum mechanics may be fairly unfamiliar. So
yeah, hold on. I promise that it's complicated. The ideas are complicated, but it's not completely unintelligible. I think average people could understand it if we're patient. But go ahead.
Well, I was going to say, in classical mechanics, the Schrodinger's cat, it's either going to be alive or it's dead. It can't be both. But in quantum mechanics, there's a scenario known as quantum superposition, because one other thing that needs to be mentioned is that, actually, I think we already mentioned a little bit, the uncertainty principle. It's always probabilities. So there's a probability the cat is dead. Let's use a less extreme example. The cat's sleeping, or the cat's awake. So you don't know. It's a combination of the two. So in quantum mechanics, it's everything is a combination, so to speak, of probabilities. There's a certain percentage probability it's awake, certain percentage probability it is asleep, and both are happening at the same time, until you look at it. And then, according to Niels Bohr's and his group's interpretation, known as the Copenhagen interpretation, the wave function, which basically describes the probability, actually it's a little more complicated, but anyways, the wave function ultimately describes the probability. According to Niels Bohr, the wave function instantly collapses to one reality as soon as an observer, such as you, open the box and see what the cat's like. Now, this presents an issue because why is the wave function collapsing, and how does the measurer, the observer, even affect the state? Like, why is it doing that? So this goes back to, and Leonard, you are trying to explain an alternative formulation of what is actually happening.
Yes, I think the modern idea now is that, first of all, the modern idea is that it's good to wonder about these kind of things. At a certain point in history, 50 years ago, physics kind of gave up on this, and you're not encouraged to investigate the nature of quantum mechanics and this reality that we're talking about. But in order to, it's looking like we need to consider this now in order to understand things like cosmology and the Big Bang and how all of that arose. But the notion about the quantum mechanics and this idea of the measurement, the idea is that the Schrodinger equation, which governs the dynamics of the wave function, actually governs the evolution of an infinite number of worlds that are all progressing at the same time, and we're in one of the worlds. And so the notion that the cat is asleep or awake occurred way back when the hammer broke the bottle. So when the hammer broke the bottle, the world split into multiple potentialities that the wave function dynamics predicts, and that we then become in one of those worlds, right? The other worlds exist in a virtual sense. We're utterly unable to communicate between these different worlds, and thus, when we open the box, we're already in the world where the cat is, say, awake.
So,
and we have been for quite some time. But these other worlds also exist, and so that's a really wild. There's a lot of people are really excited about this idea, and it seems to fit it seems to fulfill all of the requirements that we need in order to understand this interpretation of quantum mechanics.
So this seems like a so instead of, as I was saying, the traditional quote unquote interpretation, like when I took one of my bachelor's was in physics, and I recall in quantum mechanics class, we briefly talked about, here's what's happening. The wave function, as soon as you measure it, it collapses, which is the quote-unquote conventional Copenhagen interpretation. But instead of that, you're saying that there is no wave function collapse. It's real. What ends up happening is that it splits into two alternative realities, or multiple realities. Let's put it that way.
And in fact, it's multiple realities. Sometimes the cat is on his side. Sometimes he's standing up, or he's in the corner of the box. So there's so many different worlds that are splitting constantly with every single transition. This is called the decoherence. As this mixed state of the atom, either the original atom is either decayed or not decayed, so that becomes coupled with other elements of the environment that cause the different worlds to progress. There's still a problem, because this theory doesn't predict for us what our world is doing. And so I mentioned the randomness, sometimes it's referred to as indeterminism in quantum mechanics, is still a fundamental mystery. And so this many worlds hypothesis that I'm relating, that everyone's excited about, still doesn't get to the part of
let's say, if for the cat example, it may not be like 50-50 that the cat's awake versus the cat's asleep, but we don't know which way our universe will go, so to speak, right? What we are experiencing.
It does, and we're still left with probability, with determining probabilities of which world we're going to follow. So in the sense, it's sort of equivalent to the wave collapse, but it does resolve. It is more satisfying in the intellectual sense of wondering about, well, when I measure it, what does my consciousness have to do with whether the cat is asleep or not? And that was a criticism. That was why the Schrodinger cat was invented. Why that was brought up by Schrodinger was, you really believe this? This is silly. The cat is either asleep or awake. And there's something incomplete about quantum mechanics.
The traditional interpretation seems almost magical. Like, why, just because I look at it, does it suddenly shift to one reality? Whereas I agree, the many worlds interpretation, like all these realities are happening, and we just happen to be experiencing one of them. Like in a different universe, the cat say for instance, in a different universe, I'm not interviewing you, or you're not even on the show. So That's a possibility.
That's right. Yeah, I'm not on the show. Or in a different universe, I'm actually a woman. Okay.
Okay.
Or something, you know? So,
yeah. Go back. Yeah, you could be in a different unit. Wow.
Right.
I could be a girl. Wow. Okay.
And so all of the universes that are physically possible that could start, from a particular any given event. But the quantum mechanics still does not explain where the bifurcations occur.
Right.
In other words, where we go from one universe to the next.
Well, Leonard, from this, one criticism that some people might have is there's just so many universes. Like every second something is happening, and not even every second, every nanosecond or even less. Like it just keeps splitting.
Exactly. That's one criticism. One of the criticisms is it's too many universes. I don't like it.
I don't know if that's a fair criticism. I mean, in that interpretation, there's almost like there could be an infinite number of universes, and we just keep bifurcating. Now, my question here is, at one point, if we go back, like we're talking about cosmology, going back to the Big Bang, it would seem like in that initial Big Bang, there was only one universe, and then it just suddenly started splitting. Go ahead.
Yeah, that's what it would seem to be happening. Now, the thing about it is that the interesting thing about the quantum mechanics is at the time of the Big Bang, then we're talking about all of the matter in the universe, or all of the substance, energy, matter, substance of the universe is necked down to a single point in space-time, which is unimaginably dense and so forth. And so the quantum mechanics, we'd like to have a theory that would unify quantum mechanics and gravity in that case, and also the other forces that are causing this to occur. And that's still utterly not understood. However, we do observe something called cosmic microwave background, which I think we've talked about before. And
we did.
It has some fine granularity. This is the image of the universe at about 380,000 years after the Big Bang, when it became apparent. And there's a certain granularity that's seen. There's little structures, a very fine structure, and it's related to quantum fluctuations that occurred 13.8 billion years ago when the Big Bang occurred. And so it's almost like there's a kind of cosmic photograph of the universe that's frozen in time, and we see it today. So we see quantum mechanical things that we usually associate with microscopic or atomic scale things going on that are happening across the width of the universe. It's mind-boggling. I mean, it's just an incredibly fantastic idea, and so we know a lot about what happened in the early beginnings of the universe, because we understand that physics very well, but we don't understand it well enough at the point where gravity and quantum mechanics come together. We don't have a theory for that yet.
I think that's known as quantum gravity. Now, quantum mechanics can explain the other three fundamental forces, from what I understand: electromagnetism, strong force, and weak force.
Well, quantum mechanics is a probabilistic theory that talks about how transitions occur. The field theories of these different forces really is kind of a separate theory, that particles are waves in fields that permeate of the universe. But yes, the quantum mechanics governs the transitions that occur, the reactions that occur, and fundamental to it is indeterminism. In other words, there's dice being rolled. The universe generates random numbers.
Right. Hey, I know
Yeah.
we may have briefly mentioned this, but I thought one thing I always thought cool was quantum entanglement, where can you explain a bit about that? And I think Einstein had an issue with it because it allows faster than light communication.
Yeah, there's a lot of interest in this. So, in a certain respect, we can talk about the radioactive decay that creates the when we describe the Schrodinger cat problem, where we have radioactive decay that sends an electronic signal to some Rube Goldberg apparatus that breaks a bottle and makes the cat go to sleep or not in a certain period of time. Well, then the radioactive decay is a kind of entangled state where it's either decayed or not decayed, so we say that those are entangled. There's other kinds of entanglements, like various kinds of particles, like a neutron by itself, or a Higgs boson, which everybody has been talking about, will decay into two different kinds of particles. I think it's a spin zero particle, and
yes.
it will immediately decay into two different particles that have opposite spins. Okay, those two particles can fly off in different directions, but their spin is something like spin of the Earth or spin of a macroscopic particle, but they have opposite, and so the state of being opposite, not being in any particular direction, but the state of being opposite are coupled, so that if you observe the spin of one particle on one side of the galaxy, for example, you will automatically put the opposite state of the other particle. And some people have tried to understand this as like, well, John arrives every day. John always wears two different color socks, right? So if I see one of his socks, then if I see his sock is yellow, then I know his other sock is not yellow. It's not that. It's not that kind of correlation. It's a correlation that occurs at the entangled wave function, which is related to the square of a complex probability. So it's close, but it's not exactly right. And if we do experiments with a whole population of entangled particles, we find that it doesn't follow that theory of, well, the sock isn't yellow. It's not that. It's more complex than that. This was actually, and so Einstein recognized this in 1935, and he said, this can't be right, because if I measure the state of the particle in one place, then it implies, the mathematics is telling me that the other particle instantaneously assumes this state. So I measure one particle and I observe it spin in a particular direction, then I instantaneously know what the state of the other particle is. And he said that can't be right, because hey, hey, I'm Einstein. I know about special relativity, general relativity, that things can't, that information can't be transmitted
faster than light. Yeah.
But in the early 60s, there was a guy named Bell, who American, I think at Princeton, who actually came up with a fairly simple mathematical formalism calculation that could demonstrate this, and it's called Bell's inequality. And then in the early 80s, as late as that, this was experimentally verified by some a French group led by his name is, I don't know how to pronounce his, Aspect. It looks like the word aspect. I'm not exactly sure how to pronounce his name, but Aspect, and he did apparatus and demonstrated without a doubt that Einstein's objection that this influence cannot transmit at faster than the speed of light was false. That in fact the world really is weird in that respect.
So
A lot of people interpret this and say, and you see this all the time. Well, we can use this to transmit a message faster than light.
right.
The thing is that it's like that's not what it's about. It's not like you can predict what the measurement's going to say. The measurement's going to give you a random number, so it'll be 1 or 0, be up or down, right? And then from that, you will know that there's a random number on the other side of the universe that's the opposite of what you observe. So you can't ahead of time make it what you want it to be. You have to transmit the information, about what the state is that you've measured.
Right.
So you can only determine these things post hoc, as it were. I kind of think of it this way. It's like you're watching an old-time television with static, like the snow on a TV.
Yeah.
Well, that's all you have. And you know that whatever static you see on your TV is exactly the same, or it's actually exactly opposite. All the pixels are reversed from the TV that's running on the other side of the universe between these two entangled states. So the physics does not allow any information to be transmitted, but there is something in the nature of reality that is common, that is transmitted instantaneously. And I've thought about this myself, and I think that it also gets to the notion of whether there's free will, or whether all of space and time is predetermined.
Yeah.
See, one way to explain the static being the same in the two universes is that the static already exists before we observe it. In other words, so all of space, if you imagine a model of the universe, space-time, and all of the universe as existing all at once. In other words, from the beginning of time to whatever we want to call the end of time, all of that has already been determined, right? And we're just experiencing a journey through that manifold. And certainly quantum mechanics admits that, and it also explains the indeterminism. In other words, all the random numbers have been laid down throughout all of the past and future, and that they're related in that way. So now that really is going to blow people's minds, because it's almost like the idea of free will is something that philosophers and theologians have talked about for forever, and so there is some little glimmer of theoretical, or actually observational evidence that indicates that maybe we do not have the free will, and that our journey is predetermined. That doesn't mean that we're not responsible for our actions, but because it still looks like we have free will.
Well, I mean, the other thing I was thinking of is we talked about the many worlds theory earlier. So can't there be alternate, various infinite number of universes where, say, this information, like this particle is going, say, spin up, and the other particle spin down, but if you look at a different universe, it's exactly the opposite.
Well, the thing is, the Schrodinger equation is completely deterministic, and it describes a whole manifold of universes that are all progressing all at once at the same time. But and also in a certain Platonic, Plato talked about forms and virtual worlds and things like that 2,500 years ago. So in a certain sense, the reality that we have it exists. I mean, we're experiencing it. The other realities that are physically allowed also exist, and I've got air quotes around the word exist, right?
Exist.
They don't exist is not really the right word for them. They are the many possible worlds are described by the quantum mechanical description, but we're only following one, and the quantum mechanics doesn't tell us which one we're in.
Yeah, that is really intriguing. Leonard, unfortunately, for the sake of time, I am so sorry. We're gonna have to cut it off.
Tell me.
Do you have any more last sentence or two about quantum or the nature of reality?
No, we're really in trouble now because of all that wild stuff we've been talking about.
It's true. Okay, so all this stuff gets really weird, and we got all these theories. I know this stuff is explored, especially the many worlds theory. I'll just add on here very briefly that it's explored in science fiction a whole bunch, different universes. Now, from what I understand, the difference is that in the sci-fi novels and film and TV shows, the universes somehow could interact with each other. Whereas, exactly.
That would make good science fiction. If you can communicate with the other worlds, where I'm a woman,
Right.
for example.
Yeah.
Something.
I understand. So in different universe, I will communicate with a girl version of Shen. That's great. Not that's going to happen. All right. So according to science, it can't happen. So can't communicate. All right. So we're going to have to cut it off. Thank you, everybody. This is SG2 on Space. You've been listening to The Hidden World, talking about quantum mechanics with Leonard Kramer. Thank you, Leonard, for being on the show. And be sure to join us next week. By the way, follow me, facebook.com/The Shen Show. Go on YouTube, search for SG2 on Space. Support me at patreon.com/SG2 on Space. And I will end it with this. I know we haven't talked about up there in a little bit, but look up because you never know what you will see. All right? Take care.
Peace, it's Brother Atum Ra, and you tuned in to Action One Network.